the time for the Excellence in Nanotechnology Season 2 at Technical Series 2020. I'm glad to welcome you all. I would like to welcome Professor Kaushik Pal, belongs to India and born in Kolkata. He is working as a distinguished professor and group leader at University of Rio de Janeiro Biosensor Research Laboratory, RJ, Brazil. He has been a distinguished chairperson at Wuhan University, Hubei, Republic of China. He worked as a visiting professor at IIUCN, School of Energy Material and Mahatma Gandhi University, Kottayam, Kerala. He received his PhD from University of Kalyani. Most significant prestigious award, Marie Curie Experiencing Research Postdoctorate Fellow, offered by European Commission in the Greece and Brain Korea, National Research Foundation Visiting Scientist Fellowship in South Korea, active in his research career. He was appointed Senior Postdoctorate Fellow at Wuhan University, China, and within a year achieving a prestigious postage position, Chief Scientist and Faculty Fellow by China Academy of Science. Currently, he was nominated for Doctor of Science, honored award achieved from Government of Malaysia Research Institution. His current span of focusing like example nanofabrication function material, carbon nanotube or graphene, liquid crystal, polymeric nanocomposite, switchable device, bio-inspiration material, drug delivery, tissue engineering, cell culture, and integration, switchable reverse modulation, flexible and transplant electrodes, supercapacity, operator, green chemistry, and biosensor application. His superior and significant number of doctor and postdoctor research scholars with the International Institute of University. His outstanding research find out novel publication around 65 articles in several international top-tier journals like IOP Nanotechnology, Royal Chemical Society, Elvis Springs, IEEE publication, got the highest citation in every year and performed editing 25 books. He was the chairperson of 25 nation and international event, symposium, conference, workshop, summer internship organization, and himself contribute around 10 plenary, 25 keynotes, and 30 investigation lecture world over chief guest. It's my pleasure to welcome you, sir, from the Department of Nanoscience and Technology from K.S.Rangasamy College of Technology. I would like to welcome Dr. Kaushik Pal to deliver a lecture on novel switchable device implementation. So now the stage is all yours, sir.
So welcome you, sir.
Yeah, thank you so much for your kind introduction, and good evening to all of you joined this nice webinar. And thank for your kind introduction and with gathering all audience and students. And it's my immense pleasure to get an invitation from K.S.Rangasamy College of Engineering as an eminent speaker entitled the topic novel switchable device implementation. Through this presentation, I would like to share my little bit exclusive research experience. Hopefully you enjoy my session, and it will be very much helpful for students. I will start my experience skills regarding nanotechnology and how it will apply for the nanosciences. So I want to share my screen. So can you please host me to share the screen?
Proceed, sir. You share the screen.
Okay. You checked my screens, right? You got my screen?
Yes, sir.
Okay. Very nice. So once, okay. So it's in, right? Okay. So today's my topic is novel switchable device implementation. So I will discuss about little bit of application of the semiconductor nanomaterials and how it is implemented as a switchable device, optoelectronics, OLED, and everything we can discuss. So The content of my talk is a brief introduction of nanoscience and nanotechnology, which is belongs to multidisciplinary science and technologies. And my research span and activities are material science and liquid crystal embedded system, and my hand-on expertise of molecular nanostructure fabrication and molecular orientations, and several spectroscopic and microscopic investigations, and my scientific innovations and exclusive publications, and ongoing proposed research in institutional activities, patent research, project and awards and achievements. So and we will show you our group members worldwide. So what is a nanoscale? Actually, nanoscale is just nothing but one part of billion of a human hair. And these nanoscience have several branches of sciences, let's say physics, biology, chemistry, for cell tissue engineering, cell culture, bioimaging, biomedical. Every sector you can go. And is a nanorobot is a very unique application for nowadays. The blood pressure and monitoring blood sugar and cardiac diseases and heart attack. We can everything we can use by simply using of a nanorobot. And the benefit of nanotechnology is antibacterial properties of TiO2. You can see the antibacterial of human skins, which can be which can be modified by the ancient treatment. And water lily is a surface treatment of surface sealing, surface cleaning by and we can utilize the nanotextiles industry, our nanomaterials and scratch free car. Hopefully we can this we can get it. And my proposed innovative research based on nanowares, nanorods, nanoparticles, nanoflakes, nanospikes, nanocabbages, and nanocapsule. There are a lot of nanostructure we can fabricate, and we can implement it as for our novel device. And we for this utilizing this novel device, what we do, we did some by using some iridium titanium coated glass cell, LC cell, or PET sheet for flexible electronics. We can utilize it, right? So I will show you later on. What are the liquid crystal? It's a very interesting molecule. Is a distinguished phase of observation is crystalline, solid, and isotopic states. And it is a very strong molecular axis, easily polarizable substituents, and also it has some phases with temperature changes. We have different phases, schematic, semantic, nematic, and different changes of temperature. The phases of liquid crystals will change, and when we incorporate it into this nanomaterial, so it's nicely varies your optical and electrical properties. So this is our synthesized nanomaterials. You can see all together is a I just assembly of this nanostructure. You can see first in the is the zinc oxide, TiO2, CDS, and lot of nanostructures in different morphology we fabricated. I will show you later on. And this is our handmade device, which is called novel switchable devices. Is the original market cost is $1, and commercial value is a $10. So we can utilize it is very easily for the switchable device. This is I invented this device, and our experimental technique is very simplest and cost effective. So is a chemical ingredients. We started with a simple bulk powder with cadmium, zinc oxide, TiO2 bulk powder, and it is dissolved into the alkaline media, and we use sometimes surfactant for smooth growth of the nanostructure. Let's say we can utilize for hydrogen hydrate, and sometimes cationic surfactant, CTAB, for the smooth and uniform growth of nanostructures, right? So those actually prepared nanomaterials we just put into the Teflon autoclave, and we it's inside 6,000 gallon pressure, which is diminish the bulk property, and you will finally obtain the nanomaterials by several time washing of ethanol and DIO water, and you will get it like a powder form. So after that you will do for further characterizations. So you can see my when I'm starting in magnetic star. Several temperature changes you can see in the hot plate with uniform starting. So what happened, the color is simultaneously changes from green to yellow, from and greenish yellow. So you can see here our synthesized material. First is a polymer coated SiO2 substrate, glass substrate, we can see, and you can see when those nanowires come in contact of liquid crystals, it's showing just microflower like structure is evolved. And here is a right side is a zinc oxide nanorods, and porosity, some unreacted part is coming out, and some porous nanostructure is evolved. So this is a smooth growth of CDS nanowires. Let's say it's a diameter around 20 to 30 nanometer, I see. And we can see here the XRD pattern is a highest crystalline XRD patterns. And this is a switchable device, the fundamental topics which I'm talking about. So you can see here is a hot plate, and the liquid crystal molecule is vibrating when we applied the external heat, and on and off state is coming, and you can see with different temperature some droplet like structure, and sometime continuous pattern of liquid crystals is simultaneously changes. And you can see here the video, this bicapillary action inside the geometry. What happens, actually the liquid crystals flowing inside the ITO coated glass cells, and it is captured by the nanomaterials. And you can see after full capturing with by the liquid crystals, and then some switching is will start by employing some sample bias voltage, let's say 5 voltage to the cell. You can see the nice switching we captured in this video. It's called on and off states of liquid crystal. This is the beauty of liquid crystal when it is come in contact of homogeneous dispersion under nanomaterials. Then it's showing such a typical nice behavior. So this I published in IP Nanotechnology, and like let's say there are several type of droplet-like structure, shell-line pattern, and marble-like pattern. With this switching phase, we just applied our work in IP Nanotechnology. So this actually polarizing optical microscopy, and under this microscopy we can utilize the our samples for the characterization of switching. You can see the plate one at the right side is a droplet, then shell line pattern, then broken foil, and lastly plate 4 is a worm-like structure. And you can see as the electro-optical switching is at the middle. How is the switching we captured under the polarizing optical microscopy? When we started with zinc oxide nano spikes, and here is a worm-like structure. You can see the AVCM is a you can see is a HBLC, hydrogen bonded liquid crystal. So we mix the compound matrix. Okay, so Royal Chemical Society appreciate our work for the nice switching device. And this is the another system for we can make the you can see the align let's say is by spin coating, programmable spin coating coater. We use the thin film, and we growth of seed particle. In the seed particle, there is a highly aligned of vertically aligned nanowires. I deposited the zinc oxide nanowires. It's a very ultra thin nanowires. So this is the schematics, and you can see here is a bunch of nanowires of zinc oxide. And when this bunch of nanowires zinc oxide, accumulated and just it is formed like a micro-like structure, you can see. And after annealing, you can see the extreme upside is a nano rose flower-like structure is evolved. This is the series of application, morphology we can tune. So another work is a very nice work is a sodium assisted to nanotube and highly aligned nanotube array. We fabricate it and we can do some photocatalytic activities and as well as some switching, and we appreciate we published this work in organic electronics in Elsevier. So, and this is a graphene oxide. First is a graphene, and when graphene come in contact of liquid crystals, nanofiber like fiber like structure is evolved. And here is a nano ribbon. We fabricate the high quality nano ribbons, and those liquid crystal based graphene matrix we just put into our photoreflective ITO cells, and how it reacts under polarizing optical microscope. You can see there's some platelet like structure and then marble pattern. You can see the honeycomb structure is evolved in with applied several temperature, and it depends of course in liquid crystals because we use the thermotropic liquid crystals. So this is another work where is a single sample I fabricate with a nanosphere and nanocubes, nanorods together, and by the nano detector, we just interconnected all these nanostructures, and we studied some electro-optical, oscilloscope studies, and we also doped with this material some liquid crystal. This work actually influences for the liquid crystals high contrast ratio. It may enhance the display quality. You can see first first the thing we placed here is a without liquid crystals, and you can see the up structure. There is a doped with nanomaterials doped liquid crystal. How contrast ratio is increases which time we can evaluate. That is the fundamental things. And this work is published in Materials later. Is a switchable and self-assembled CDS nanowatts embedded liquid crystal cell for high performance static memory, or you can also use as a static memory. So is a is another work is a, you can see the first one is a graphene structure, and then we uniformly dispersed into CDS nanowatts. Then all those combined materials we placed into the homogeneous dispersion under liquid crystals. You can see the nano forest like structure is evolved, is a nano tree, let's say. So those samples hybrid compound we put sandwiched inside the cell, and we can observe the same electro-optical switching. You can see, and also we take the characterization of CV and IV. You can see the hysteresis peak is coming, and the several cyclic pattern is coming from hysteresis loop of CV responses. So this work is published in organic electronics. Our experts and me, we work for the stretchable electronics. You can see we developed these ideas in this work. And is another work is a smart implant switching of embedded liquid crystal matrix, and same thing is happening but different material and different size of nanomaterial, and you introduce different kind of liquid crystal into, and we take the CAFM, I mean contacting mode of CAFM, how much current passing to the surface, we just measured by this. And this work is appreciated by organic electronics, is a smart implant switching of embedded liquid crystal matrix. And you can see is a solar cell. Our group is performed this nice work is a AG nanoparticles is for the solar cell fabrication, and you can our group is synthesized all this material, and we published it in nanostructure and nano objects. So yeah, another work is virus-like nanoparticles as a novel gene therapy. We can utilize it, and you can see the our work is appreciated by the biochemy. It's my USA group and some Malaysian group is working for the virus-like nanoparticle, working for the delivery tool as a gene therapy. So several sector we can utilize our high yield nanomaterials. So, and so this is the switchable device we implemented by, you can see the several stages we maintain. First, the spacer, we use the spacer, then liquid crystal growth, and then we can place the CDS nanomaterials, and we sandwiched it. And what happened inside the microscopy, we will see the nice switching. So this switching is coming only when the nanomaterials and liquid crystals is perfect ratio and homogeneous perfect dispersion. Without this, we cannot get the switchable characteristics. So it is very much important to get this. And this work is also, another work is appreciated is a graphene nanowires and graphene, Janerio and nanowires and graphene dispersed liquid crystals for switchable device modulation from UK group and USA group associated with me and work for this. And this is the in-depth study of liquid crystals. We can see the some simulated patterns we just analyzed and understand under the polarimetric microscopy, as well as we also investigated the switching effect, you can see. And different layer structure in the vicinity of the elementary dispersion course of the strength of the liquid crystal molecules. We how it is oriented inside the cell in confined geometry inside the photoelectric cell. We can work for this. And this work in different countries of people associated with me, and we just published this work in electronics materials later. So this is my recent work publication in journal, organic electronics. It's a bent core liquid crystal, the different type of liquid crystal showing the nice characteristics of when it is come in contact of graphene and as well as liquid nanomaterials. So this is our another work for polymer based work in published in scientific reports. And this is my published book in 2019 to 20. We published our a lot of books, those on based on nanomaterials, green nanomaterials, polymer, and my ongoing research based on superlattice. You can see the this is we can take the some switching and some thermal study. This work is my going on, and my ongoing work on also graphene as a stretchable electronics, and also how to make more advanced switching. I'm just trying for this. And this is a fundamental study. You can see the polymer dispersed nanomaterials and graphene introduced by introducing graphene with biochemical etching. This is the inner geometry, how we chemically react and make the etching process. And this is our schematics. And you can see just this is my work on switching. You can see multiplex GOLC is the graphene dispersed liquid crystals, and polymer when it is come in contact of polarizing microscopy, there are different phases is coming. So and you can see the switching, how the switching is the internal geometry I showed. And my current work based on green synthesis of because if you synthesize of let's say gold nanoparticle by your starting material is ascorbic acid, which is very very costly right now, but we can get it from termine food by chemical reaction process. And we can this gold nanoparticle we can utilize for the drug delivery, cancer nanotechnology, nano imaging, biosensor, anything we can use it. And I should acknowledge my research groups. Those people are associated with me in collaborations. And this is my postdoctorals. And PhD scholars in several countries. We are working together for the active research and innovative research publications. And I would like to, I just published a few articles and working for new invention. And this is my institutional academic achievements. I just launched MTech in nanotechnology with collaboration with another country of research institute and universities, and it's called Sensor Nanotechnology and Faculty Exchange Program, Summer Research Program. There are a lot of schemes is there, and this is our roadmap of how we'll start from 2020 to 2030, our plan of work. And this is some research schemes. We are going to Sparks, Perak, GAN project, Impress project in India, and collaboration with different countries, which is for the funding I'm talking about. And this is the our erudite professors from different country, and Professor Rao came with our institute, and there we are work together. And I have MOU with the different countries, and we can utilize their product. We can utilize exchange our ideas, and we can exchange our some projects. And there are international collaboration of different universities, people's associate with me for supporting research all time. And this is already announced. I just my little bit award, and this is my award for International Asian Academy of Science Congress from University Jordan, and another award from European Union is the University of Marivar, Slovenia, and another award from USA Chip Tubes company as a distinguished scientist, and my recent awards for DSC from Malaysia. And this is our professional research visit and MOU. And you can see that our different students and different faculty member working with me, and they visited my place. Sometime I'm going to there, and I should acknowledge all those persons, those who are invited me as chief guest in worldwide, and we did MOU various institute. We can see, and thank you very much for your kind attention.
Thank you so much, sir. So, Kanakulanji?
Sir?
Yeah.
Thank you, sir, for your valuable speech. It's an eye-opening speech. The next session will start sharply at 7 o'clock. Thank you.
Yeah.
So, any doubts? Please ask. Thank you so much, sir.
Okay, thank you.
Thank you so much for your valuable presence. Thank you, sir.
Okay, bye.
Thank you, sir.
Hello.
Yeah, tell me, ma'am. Ma'am, I think sir left right.
Sir, is there any working process in biomedical in these liquid crystals?
1 second, ma'am. Sir, I think Kaushik sir is left. Yeah.